Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson we were talking about angular displacement and angular speed. And if you remember, we said angular displacement, it is an angle through which a point, a line, or an object that is rotating through a specific, you can say, direction, and also around a specific axis, you could say, and it was measured in radian. On the other hand, angular speed, it was the time rate of change of angular displacement, or we said that it is the ratio of the change of angular displacement divided by the time. And then, of course, we went through some examples, the equation and everything. Now, today we'll talk about the angular speed of some of the objects that have a constant angular speed. What do we mean by constant angular speed? That means they have a fixed angular speed. Their angular speed is not going to increase or decrease. In other words, while they're rotating or spinning, their rotation or spinning, it is not going to increase or decrease. And what are some of those things here? The first thing that we have is, we're going to talk about this one. Angular speed is constant for the following cases. The first case that we have is, we can say the second hand, the minute hand, the hour hand, Earth's rotation and Earth's revolution. All of these have a fixed or a constant angular speed. What do we mean by this? Let me explain furthermore. Now, the first thing that we have is this one. So let's talk about this one. When we have, let's say, the hands of a clock. So we're going to, let's say, take three examples here. Let's say these are the hands of a clock. Let's just get back this one here, the hands of a clock. First of all, let's just draw maybe three circles here. Okay, and this is one more. Of course, later on we're going to let's say we're going to talk about the other cases where the angular speed is constant as well. But the first thing that we have is this. Now you know that the clock has three hands, yes, and that is the second hand, the minute hand, and the hour hand as well. We know that. Let's just say this is 12, this is 3, 6, and 9. This is a clock. What are the hands of a clock? Let's just say the first one is the longest, and that is the second hand, let's just say. And then another hand that we have is, let's just say, the minute hand, that is shorter than the second, and then we have the hour hand, which is the shortest at this case here. So now, as you can, for example, if you have a clock, let's say in your room, or even, for example, if you're wearing a watch, if it is not electronic, you can see that these hands are moving in a circle without speeding up or slowing down ever, unless the battery is dead, but that is a different situation. So when the clock or when the watch is working, let's say normally, then of course these hands are always move or rotate with the same angular speed. But how do we know how fast they're rotating? We know that every time. So let's just take the second hand as an example first. So once again, the second hand. For the second hand, right, as an example, now we know that in order for the second hand to make one full rotation, that would be angular displacement, right? So we can say for one full, let's say, rotation, so delta theta, in this case, it is going to be 1 rev, right? But then how long does it take to complete one full rotation? Remember, this is the second hand, yes? So it is going to take 60 seconds to make one full rotation. So if we ever want to find the angular speed for the second hand, we'll say omega, that is equal to delta theta divided by what? Divided by the delta time. But once again, so the delta theta here, can I say one full rotation, that is 1 rev? Yes, well done. Divided by the time that it takes, which is 60 seconds. But now, one more time, we know that every rev, it is equal to what? It is equal to 2 pi. So you could just say 2 pi instead of multiplying by 1. And that is just 2 pi. Divide by what? Divide by 60 seconds. So once you do the math, you will get angular displacement. That is approximately equal to 0.105. Remember, that is radian per second. This is, we can say, the angular speed for what? For the second hand of a clock. Okay, now can we find the angular speed for the minute hand of a clock? Yes, we're going to do exactly the same thing here. So at 12, that is 3, 6, and 9 here. Now this time we're going to find the angular speed for the minute hand, don't forget. So we're going to use the same procedure. Angular speed, it is equal to 1 full rev. All right, that is the angular displacement if it is making 1 full cycle here. So we'll say 1 rev, but divided by the time it takes. Remember, how long does it take the minute hand to make 1 full rotation? That is 60 minutes. But you do know that we're not using minutes, right? We have to convert minute. We know that. How do we convert minute to second? We'll just multiply by that, by 60. So 1 rev, that is 2 pi here. And then 60 minute, each minute is equal to 60 seconds. So once you find the angular speed for the minute hand, you'll find out it is equal to what? Get a calculator, do the math. In this case, of course, we will get, or we're going to get 1.75, yes? Let me get a calculator. I think it's better. So that is 175. I remember that one, but all right. So just 2 pi divided by 3,600. That is clearly, let's just change this one to scientific. Wow, I've just turned the calculator off. Isn't that odd? Okay. So we'll say 2 pi again divided by 3,600. The answer is going to be 1.75 times 10 to the power negative 3. That is going to be radian per second. That is the angular speed of the minute hand. What about the hour hand? We're going to do exactly the same thing. Okay, this time for the hour hand, this is 12. Remember, 3, 6, and 9. But look, there is one thing you have to be aware of this one here. Angular speed, it is equal to 1 rev again, because that is how much it would be if it is making 1 full cycle, that is 1 rev. But how long does it take for the hour hand to make 1 full rotation? Remember, it is 12 hours, not 24, because if it is 24, that is going to be 1 day, and we don't want that. So 1 rev divided by 12 hours here. So now, once again, 1 rev, that is 2 pi, you can say 12 hours. Each hour is 3,600 seconds. So you could just do the math in this case. This time, we'll say 2 pi divided by 12 times, we can say 3,600. The answer is going to be 1.45. So we can say angular speed for the hour hand, this is for the hour hand, it is going to be 1.45 times 10 to the power negative 4. That is radian per second. This is how you can find the angular speed of clock hands, the second hand, the minute hand, and the hour hand. Remember this, in order to find the angular speed, it is always, we're taking clearly the angular displacement for 1 full rev, let's say. So 1 full rev divided by the time it takes. What if we take 2 revs, for example? There are some students who says, so what about if I take 2 rev? Well, at any point here, let's say, or it could be even this point here, if you take 2 rev, right, how long does it take to complete 2 rev? It is going to take 2 times 60 minutes. But again, this 2 will always cancel out, then you'll get the same answer. What if it is 100 revs or 10 revs or 100 times, you'll have to say 100 times 60 because every rev takes 60 minutes. But again, they'll cancel out, so it is exactly the same as if you take 1 rev, divide by 60 minutes, then you convert the minute, and this is how you do that. Well, these are for the hour, let's say, hands. Do we have anything else where the angular speed is constant? The answer is yes, and that is Earth's rotation and revolution here. Now, we know that Earth rotates on its axis. So, but if we take the time for 1 complete rotation, let's say, so we'll say angular speed for Earth's rotation here, it is equal to, again, 1 rev. That'll be, let's just start with this, that'll be delta theta over delta t. But then, how long, like if it is completing 1 full rev, that'll be 1 rev, 1 full cycle, divided by the time. How long does it take the Earth to make 1 full rotation? That is, remember, that is 24 hours. Now, once again, 1 rev, it is equal to 2 pi, 24 hours, convert that to second. How do you do that? Every hour is 3,600 seconds. Once you do the math, of course, you'll get the answer. Let's do this one too. We'll say 2 pi divided by 24 hours, every hour is 3,600 seconds, then the answer you will get it is going to be 7.27 times 10 to the power negative 5. That is going to be radian per second. This is the angular speed of Earth's rotation. But we do know that Earth has two types of motion, right? One of them is rotation, the other one is revolution, where the Earth revolves or orbits the sun here. Let's say this is the sun and this is the Earth in here. Once again, so if I want to find the angular speed of the Earth's revolution, once again, we'll say that is delta theta over delta t. Now, if we take, for example, one full rev, one full cycle, that is 2 pi. Okay, divided by the time it takes. Normally, how long it takes the Earth to complete one full revolution will be given, and that is, this book uses 365.25 days as well. And let's say 25 days here. So now, but of course, we cannot use days. We'll just convert this to second here. So once again, 2 pi, we know that every 300, like in 1 year, there is 365.25 days. But you do know that every day it is 24 hours, and every hour is 3,600 seconds. So once you do this, you will find the answer, which is going to be, let's just do that too, 2 pi divided by 365.25 times every day is 24 hour and every hour is 3,600 seconds. Once you do the math, you'll get 1.99 times 10 to the power negative 7. That is going to be radian per second. So these are the angular speed, let's say, or the, like for example, for some of the objects that have a constant angular speed here, that means they're not going to rotate faster or slower. By the way, this could be the rotation of anything else. If they tell you that this thing is rotating, let's say uniformly, or let's just say has a constant angular speed while it is rotating around something else, then you can always take delta theta as 1 rev, let's say, divided by how long it takes to complete one full rotation. Then you can always find the angular speed of that object here. So now let's summarize what we have learned as well. So we said the angular speed, remember this, the angular speed for the let's say hands of a clock, whether if it is the second hand, whether if it is the minute hand, whether if it is the hour hand, these are all constant. And how do we do that? We'll always say, right, one full rev, that is 2 pi divided by the time taken, which is 60 for the second. For the minute, it's 2 pi divided by 60 minute, but don't forget every minute is 60 seconds, so you could do the math. For the hour hand, again, it is 2 pi divided by 12 hours, every hour is 3,600. So you don't have to, a lot of students say, Mr., what if I memorize this? You don't have to memorize this, because by the end of, for example, let's say this academic year, of course, there are tons of stuff that you've memorized. So chances are remembering this during the exam while you're under a lot of pressure are very, I don't know, chances are you're not going to remember that well. But if you know the procedure here, like how you can get it back, it is always 1 rev, which is 2 pi divided by the time they take. You can easily get it back, let's say, in a second or two. So remember, the angular speed for the hands of, let's say, the clock, these are always constant. And we said the angular speed for Earth is rotation, and revolution is also constant here. So once again, that is 1 rev, or you could just say 2 pi, let's say, divide by, for rotation, we said it takes 24 hours, every hour is 3,600 seconds, and you can simply do that. For revolution, it's going to be the same thing, but this one is 365.25 days, every day is 24 hours, every hour is 3,600 seconds. You just do the math, of course, you will get the answer always, almost like instantly here. All right, this is all regarding those objects that have a constant angular speed. I hope you keep practicing them, and then you can always get them back very, very easily here. Okay, now let's get back to this one here. By the way, there is one thing actually I haven't mentioned here. So let me take you back to perhaps what we just went through here. We said previously, if you remember, we said if an object is rotating clockwise, Okay, we said delta, or let's start with arc length, is negative. Delta theta is also negative, and angular speed is also negative. But I don't know if you've noticed or not, for the, let's say for the hours, for the hands of a clock in here, I didn't use any negative values, or I didn't put in any negative in front. And have you ever wondered why I didn't do that? Well, there's one thing I would like to be very specific regarding this. Do you know what is the purpose of using negative or positive values? We only use them to determine the directions. So for example, when we say something is, let's say something is rotating clockwise, we put a negative so that we know which way it is rotating. When we say something's rotation is positive, that means it is rotating opposite to a clock. So the only purpose of doing negative and positive to say which way they're rotating. But think about this. How many ways can a clock ever rotate? It is only one way. So if something has one way to rotate, do you think we even need to tell which way it is rotating? So no. So this is something that we can do. A lot of, like in some other cases, you might say it is a default rotation. This is why we're not using negative. Let me get back to the point again. So if something is rotating in only one way, you don't have to say positive or negative, because the purpose, again, of positive, negative, to tell which way is rotating. But if there is only one way to rotate, we don't need that. This is why we never use negative for the rotations, let's say, of the clock hands, whether they are positive or negative, even for the rotation of the Earth, whether if it is rotation or revolution, because there's only one way, we don't have to say positive or negative, because the answer is always, the direction of rotation is always obvious which way it is rotating. So these are the values that we just went through. Remember, this is the second hand, and this is the minute hand, and this is the hour hand. Earth is rotation and revolution. It takes 24 hours to make one full rotation, 365.25 to make one full revolution here. I hope you practice those until you get really well, and this is the reason I left a note why we did not use negative for the motion or the angular speed of the clock hand, let's say. Now, we have a question here. It says what? It says, how long does it take the second hand of a clock to move through 4 radian here? Now, I want you to be very careful here, because you will be asked questions like this, perhaps a lot here, okay? So how do we know this? So first of all, it says, how long does it take? So delta t is unknown, you do know that. It says, it takes for the second hand. So which hand of a clock? The second hand, to move through 4 radian. Is this delta theta? Yes. So remember this, the angular speed for the second hand, it is equal to delta theta over delta t. Now the question says how long does it take? So the delta t is unknown. Delta t here, it is equal to, you could just switch this to here, it is equal to delta theta over angular speed for the second hand, yes? Now, what is the angular displacement? I hope I didn't say that incorrectly. So at delta t, it is equal to angular displacement divided by the angular speed. Yes. Now, what is the angular displacement for the second hand that is travel? It says 4 radian, and that is 4 radian here. Okay, no need for the radian here, just 4 in this case here. What about the angular speed? In order to find delta t here, you need the angular speed. But is it given? The answer is no. Have you memorized? The answer is no. Do you need to memorize? The answer is no. Okay, so we'll just say, for example, because you need the angular speed of a clock hand, you have to find it separately. So how do you find the angular speed of a second hand? We just said that the angular speed it is equal to 1 rev, that is 2 pi. How long does it take to complete one cycle? 60 seconds, and that is approximately equal to 0.105 radian per second. Now, this is how you can always get it back very quickly as well. So now just plug this into the equation, divided by 0.105, and then of course you can find out how much time it takes, which is about 38.1 seconds. This is how you can instantly answer the question. Not just this, it could be any other questions. So expect questions like this in Wizati, because these are very easy to do them. Once again, angular speed will never be given for these cases, but you can always find it without any problem. Okay, so this is how we do that. First of all, you can find the angular speed and then just do the math. You will do that. Now there is another question here. This is also very easy. It says find the average angular speed of the Earth about the Sun. Okay, in radian per second, it gives you a hint as well. It says Earth orbits the sun once. What does it mean, orbits the sun once? Does that mean 1 rev? Orbits the sun once, that is 1 rev. So we can say delta theta, it is equal to 1 rev. And then in what? It says every 365.25 days. Is this the time for how, like for example, the revolution? Yeah, so we'll say delta t, 365.25 days. Now, can we find the angular speed for the Earth? Absolutely yes. And how do we do that? Let's just write it somewhere here. Okay, so we'll say angular speed, it is equal to, angular speed of the Earth is, let's say revolution, it is equal to delta theta over delta t. Now delta theta that we have, it is 1 rev, which you do know that every rev is 2 pi s, so you could just 1 times 2 pi, that is still 2 pi radian, divided by how long does it take? 365.25 days. Every day is 24 hours, and every hour is 3,600 seconds. I should have done it, wrote it below somewhere, but that is totally fine. So once you do the math, of course, you'll get 1.99 times 10 to the power negative 7. It is going to be radian per second, and that is how easily you can find the answer. Now we have a few Uzadi questions. Remember, the questions you will be asked is exactly going to be like those questions here, because these are the past Uzadi questions. So how do we do this? Let's solve a few questions here. And then the first one that we have, let's just take it a step further, let's say. Let's get this one back again. All right, that is what we have. Just this one a bit bigger. Oh, it is gone again. Okay. I think we'll have to move it up a little. Okay. Now, I want you to be focused a little at this point. Let's see if we can do that. Oh, that's even smaller. All right. Now, I want you to focus at what I'm doing here in order to answer those questions that are here. Okay, so the first thing that we have, what does it say? Okay, it says the Earth is rotating. So let's just move this one up a little maybe. Okay, so it says the Earth is rotating. Earth rotates 360 degrees. 360 degrees, isn't this the same as saying 1 rev? Well done, yes, and that, indeed it is actually. So that is what we have, 300. Once again, Earth is rotating 360 degrees. That is, we can say delta theta here. So delta theta, 360 degrees, which is the same as 1 rev. You don't have even to say rev. Isn't that the same as 2 pi radian? Yes, well done. So these are all the same thing. It says every 24 hours. Wow, this is something new, I guess. Okay, I think we'll have to stop writing on that thing. All right, so let's get it back here. So Earth is clearly rotating this much in 24 hours. So we can say delta t is 24 hours here. What is the angular displacement here of a person standing on the equator for only 3 hours here? So once again, remember the question says, what is the angular displacement, delta theta, for a person standing there for 3 hours? That means delta t is 3 hours. Now we do know that because delta theta and delta t is given here. You might say, what about this one? I'll tell you about this one in a second. But if they ever ask, for example, for this, we know that average angular, or you can just say angular speed for the Earth is rotation here, that is equal to delta theta over delta t. Here the question says, how long does it take? So, it says, what is the angular displacement? So delta theta, it is equal to angular speed times delta t. You agree, right? So now, once again, let's just remove this one a little bit. Once again, delta theta, it is equal to, but here's the thing. The time says for 3 hours, so here's 3 hours. Clearly, you have to convert to seconds, right? So we'll say, one more time. This is the 3 hour. Each hour is clearly 3,600 seconds. Yes, you agree. 3,600 seconds here. Now, let's just remove the second for now so that Okay, you don't get confused. But now we need angular speed for the Earth's rotation. Do we have angular speed? No. But if you look at the first part of the question here, they gave you this much. It says, the Earth rotates 360 degrees in 24 hours. Can I use this piece of information to find the angular speed of the Earth? Once I find it, then I can use that over there. Yeah, so angular speed, it is equal to 360 degrees. That is, if you convert to rev, that would be 1 rev. In radian, that would be 2 pi. And you can do that too here. Okay, divide by the time. How long does it take? 24 hours. But every hour is 3,600 seconds. So once you do the math, what is the answer that you get? Let me get the calculator back in here. Okay, so that is 2 pi. I'm doing this so that you can do exactly what I'm doing here. Divided by 24, and every 24 hour it is equal to 3,600 seconds. So the answer is going to be 7.27 times 10 to the power negative 5. Now all you have to do, just plug in this number or bring this number into this part of the question here. So once you do that now, we can just write it here. 7.27 times 10 to the power negative 5, and then multiply by this much. So once you do this, of course, you'll find the angle here. So let's just do that. 7.27 times 10 to the power negative 5 multiplied by 3 times 3,600 seconds, the answer that you're going to get it is 0.785. So delta theta here, it is going to be 0.785 because it's delta theta, so it is going to be in radian here. So now let's take a look if we have this in the options. Do you have 0.785? Yes. If you round this one up, of course, this is going to be the same as 0.79, and this would be the correct answer. So if I write on this, of course, this whiteboard is going to, let's say, disappear, but I guess we don't need it anymore here. So that is, all right. And that is basically what we have. Oh, still not writing. Okay, so let's just get this one back. Let's just move this one away. Now, of course, we can write here, and that is the correct answer that we have in here. Now, if you take a look at the second question, it says, what is the angle that the second hand of a clock rotating 10 seconds here? Now, that is new here. Okay, so this time, I'm not going to do the same thing. I'll just, move to the whiteboard and show you how this one can be done very, very easily here. So, again, how long, all right, or what is the angle that the second hand of a clock can move in 10 seconds here? So in 10 seconds, what is this angle that it covers? We know that angular displacement or angular speed, it is equal to angular displacement divided by the delta time. So now it says, what is the angular displacement? So delta theta, it is equal to angular speed times delta t. And the time that we have, it is just 10 seconds. But do we have the angular speed for the second hand of a clock? The answer is no. Can we find it? Yes. The angular speed for the second hand, it is 1 rev over the time. So I'll just say 2 pi divided by 60. Isn't that 0.105? Yes. Now all you have to do, just write this number here. 0.1 or 0.105 here times 10, that is going to be about, let's say, 1.05, and that is angular displacement, so this is going to be in radian. This is how you can do that very easily. Okay, now let's get back to the next question that we have. What does it say? So that was oh, there's one more thing, as a matter of fact. It says, what is the angle? If you look at the choices that I have, these are in degrees. And what was the angle that I just found here? It was in radian, if you know that. Let's go back to this. See, isn't this in 1 radian? But if you saw the options were given in degrees. Isn't that another, or doesn't that mean I have to convert radian to degrees? Yes. And how do you convert 1.01 radian to degrees? We said that whenever you have radian, like fast forward, you could just multiply by 57.3, and that is about going to be what? Because that is this 0.5 here, it is going to be about 60 degrees here. So once you multiply, you get this one here. So let's get back to the choices, and now you can see if we have 60 degrees. Yes, we do, and that is going to be option C here. All right, so that is the answer. Okay, now here's another question which is very similar to that, but this time is opposite. It says how long, so they need delta time, does it take the second hand of a clock to move through 30 degrees here? Okay, so this time, we'll just do that here without going so that we can still see the choices or what choice. This is in second here, so that is way easier. But let me just tell you how we could do this very easily. Once again, it says, how long does it take the second hand, one more time, of a clock to move through this time 30 degrees? So once again, omega, that is for this question here, or angular speed for second hand, it is equal to delta theta over delta t. Do you agree with me? This is for the second hand. And then we want, it says how long does it take? So we want delta t. Delta t, it is equal to, just swap this straight here, switch them. That is delta theta over angular speed, but angular speed for what? For the second hand, yes? It says, but look, this delta theta here, this time, it is given in degrees. Can I use degrees in calculations? No. Well done. So are you saying first I'll have to convert the degrees to radian? Well done. But how do we do that? We simply just divide the degrees by 57, right? So here's delta theta. If I do that here, it is equal to delta theta. It is equal to 30 degrees. Just divide by 57.3. We get the answer in radian. So let's see what it is. The answer is going to be 0.524. 0.524. That is going to be in radian here. Okay, now that is 0.524. Okay, in radian, divide by the angular speed. But do we have the angular speed for the second hand of a clock? The answer is no. Once again, you will have to go and find it, yes? And how do we do that? We said to find the angular speed for a clock hand here, we always say 2 pi over the time it takes, or 60. So once you do this, you get about 0.105 here. Now you can do the math and find the answer. 0.524 divided by 0.105, and then of course the answer that you will get, it is going to be about 4.99, which is about 5. Do we have 4.99, which is about 5 seconds here? Yes, and that is option A. This is how you can do all the questions without making any mistakes here. I believe you could do the rest of the questions that we have them here. Now we're going to go to a new concept, and that is angular acceleration, or you can say, let's say, the rate of the variation of the angular speed. What is angular acceleration? Now let me take a step back, or perhaps to grade 11, let's say. In grade 11, we had acceleration. If an object were going from point A to point B, and along the way, if the object were, let's say, it was starting with, or at this point it has an initial speed. If the object was going to, for example, or was speeding up, at this point, final velocity or the speed would be higher. So in order to find the acceleration, we were saying acceleration, it is equal to the change in velocity over the time. Or we were saying V final minus V initial divided by delta t. That is how we used to find acceleration. And remember, acceleration was measured in meter per second squared. But remember, that was grade 11. That was for translational speed, you can say, or motion, not speed. And that is when objects are moving in a straight line. But you do know that this year we're dealing with angular quantities because objects move at some angle here. So now, if we're going to deal with angles here, so instead of acceleration, we're going to use angular acceleration. So this acceleration that we use are going to become what? In rotational here. So let's just write this. We have angular acceleration. Angular what? Acceleration. What is the symbol that we use for angular acceleration? It is a Greek letter. It is called alpha. But we don't normally say alpha. We still call it angular acceleration. Isn't this the same as this? So we'll say angular acceleration, it is equal to, we can say the change in angular speed divided by the time, or you could say omega final. Isn't that the same as this here? Omega final minus, instead of using, let's say, linear quantities or variables, we're going to use angular ones. Minus omega initial divided by what? Divided by delta Excellent. Now, of course, what do you think the unit of angular acceleration is? We do know that the unit of angular speed, that is radian per second, and then divided by the time, which is second, so radian per second, that becomes radian per second squared. And you can see that here's meter per second squared, here's radian per second squared. So that is pretty obvious up to this point. But if you look at the equation, how can you translate or use this equation as a definition for angular acceleration? Well, it's pretty simple. If you remember previously, we said anything divided by the time, we can say the rate of. Do you remember? The rate of. So, something divided by the time, the rate of. Can I say here for the angular acceleration, it is the rate of because it's divided by the time? Yes. And you do know that this symbol, it means the change, right? Sometimes it could mean the difference too here. Okay, so can I say the rate of change of angular speed? Yes, and that is exactly the definition of angular acceleration. I'll repeat the definition again. We'll say angular acceleration, it is the rate of change of, let's just say the rate of change of angular speed, and that's it. So once again, the rate of, why? Because it's divided by the time. What is divided by the time? The change of angular speed. So the rate of change of angular speed. And it is measured in radian per second here. That's one thing. Last year we said acceleration is a vector quantity, this year too. So one more time, do remember previously what we have said earlier. Let me just clean this one here. So we said that if an object is moving in a circle here, we said the arc length was negative, right? Let me just go ahead and write all this here. So the arc length were negative, the delta theta, angular displacement was negative, angular speed was negative if it was clockwise, right? Now we can add the angular acceleration too. That is also negative if the rotation is clockwise. What if the rotation is counterclockwise? Then all these, of course, are going to be positive here. So angular arc length, angular displacement, angular speed, and then now angular acceleration will be positive too. But then there are some keywords I need you to be aware of them. And what are these keywords? Perhaps before the keyword, remember this. Let me write the equation one more time. Angular acceleration, we can say omega final minus omega initial divided by delta t. Remember, we can only use this equation if omega, or angular speed, it is measured in radian per second. What do we do if it is not measured in radian per second? Like rev per minute or whatever, then you convert to radian per second, then you can use this in calculation, and that's it. All right, now here's the thing. So remember, what if there are some keywords you need to know? The first thing is, we said that angular acceleration is a vector quantity. That means it can be positive or negative. Second, what do you do if the question, for example, says an object starts from rest? Whenever it says starts from rest, let's say from rest, that means, remember, starting from rest, that means omega initial is 0. What if it says comes to a stop? Right? Comes to a stop. That means it is going to slow down until it stops. Can I say omega final is equal to 0? Yes. Excellent. Now, that is basically starting from rest, omega initial is 0, comes to a rest or to a stop, comes to a stop. That means omega final is 0. But there is more to this. We know that if an object is moving in a circle, all right, let's say at this point, it goes to point B here. Clearly, this point has an initial angular speed, and at this point has, let's say, omega final, let's say, or it reaches an angular speed at this point here. We know that if omega final is bigger than omega initial, what does it mean? That means the object is speeding up, yes or no? Because clearly, if an object is speeding up, this angular speed is going to be smaller than angular final. So, if it is rotating, watch this, because this is very important here. If omega final is bigger than initial, then that means the angular acceleration is positive, remember, only if the rotation is counterclockwise. Because if you want to find angular acceleration, omega final minus initial, divide by delta t, let's just give a number, for example, 15, and this is 10, you get a positive number. Divide by whatever the time is. Okay, now, what if For example, at this point, we have a certain, let's say, speed. Let's just say this time is 15. For example, it ends at this point, but the angular speed is 10. In other words, we can say, what happens if omega final is smaller than omega initial? Can I say the object is slowing down? Yes, because final is smaller than initial. And if the object is slowing down, that means angular acceleration will be negative. Don't forget. So based on this, right? But remember, the angular speed is still positive here. So now at this point, just remember one thing. Or you can say during speeding up, the angular speed and angular acceleration will always have the same direction. But while slowing down, they will always have opposite direction. And what does that mean? That means if the angular speed is rotating clockwise, and that is positive, but if it is slowing down, then angular acceleration will be negative. But what happens if the rotation is clockwise? Have you ever thought about this? If the rotation is clockwise here, that means angular speed is, let's just say we start at point A, we'll end at point B here. So we know that angular speed is negative, right? So let's just say if it is going to speed up, remember, if it is going to, let me just write down. In speeding up, we can say angular, let's say speed, all right, and angular acceleration will have the same direction. Doesn't matter which way they rotate, clockwise or counterclockwise. So if it is counterclockwise, let's say if it is clockwise, that means angular speed is negative. It is speeding up, even acceleration will be negative. And of course, you could take some numbers just to prove that. If the rotation is counterclockwise, they will be both positive. Okay, and we just showed that. But what about if the object is slowing down? So we'll say in slowing down, let me just write this. In slowing down, they will be opposite. Remember, they will be opposite. What do I mean by opposite? That means, watch this. Here's, let's say, that is slowing down. If angular speed is positive, then angular acceleration will be negative. What if it is, for example, the opposite? If the angular speed, let's say that is in slowing down. If the angular speed is negative, then angular acceleration will be positive. Let me tell you what I mean by this. Here's the same object or circle again. This time, if an object is moving clockwise, we know that angular speed is going to be negative. Starting from point A to point B here. Okay, so if you want to find angular acceleration, omega final minus initial divided by delta t. If it is going to speed up, omega final will be bigger than omega initial. Let's just say this is negative 15 because it is clockwise. This is negative 10. So if you just plug in the numbers here, let's just write here. So we'll say negative 15 minus negative 10. See? But this negative cancel out. So negative 15 plus 10 here. So the answer, whatever the time is, we're going to get a negative acceleration because the object is speeding up. Didn't we say in terms of speeding up, they will always have the same direction? Okay, that is the note that we just set it up here. Okay, what about if it is slowing down here? Let's just say the motion is, or the rotation is clockwise. That means omega is negative, but watch this. If it is going to slow down, let's just say at this point the angular speed is 10, and at this point the angular speed is 5. It is slowing down, yes, you can see that. But because the rotation is clockwise, these are both negative. And if you want to find angular acceleration, you would say final minus initial divided by delta t. Now, what is final? Negative 5 minus, what is initial? Negative 10. Negative becomes positive. That is the same as if you say negative 5 plus 10. So we get a positive 5. And divide whatever the time, doesn't matter. So we get a positive number. Do you see the thing here? Okay, so I think I explained too much. If you didn't understand this, that's totally fine. Just remember this. When an object is rotating, It doesn't matter which way it is rotating. If the object is speeding up, the direction of the angular acceleration will always be the same as the angular speed. But if the object is slowing down, no matter which direction or which way the object is rotating, the angular acceleration will be opposite to that, period. Well done. Okay, and then, of course, I'll leave the detail for you to go through them one more time if you didn't understand this. Okay, now, but there is one more thing I would like to point out in here. What about the angular acceleration for those objects that do not speed up or slow down? Well, we have an answer to that as well. We'll say, what about for those objects that have a constant angular speed? Like what? Do you remember the motion of the clock hands we said? Do they ever speed up or slow down? The answer is no. So can we say they always have the same angular speed? The answer is yes. So what do you think their angular acceleration is? 0. Why? Simply because they don't speed up or slow down. Do you want me to prove that? Let's just say angular acceleration, we know that it is equal to final minus initial divided by delta t, yes? So let's just use an example like an easy number. Let's say, because they don't speed up or slow down, so whatever initial is, final will be the same thing. Let's just use random numbers. Because the angular speed doesn't change, so 10 minus 10, that is going to be what? Isn't that 0? So 0 divided by whatever the time is, we will always get 0. So based on this, we can say, that actually just contradicts with the definition. Because we said, angular acceleration is the time rate of change of angular speed. If there's no change in angular speed, there is no angular acceleration. So we can, whenever you're given, for example, examples or questions like, what is the angular acceleration of the clock hands, whether for the second hand, minute hand, hour hand, the angular acceleration of Earth's rotation or revolution, you can right away immediately say 0. Why is this 0? Because they don't speed up or slow down. So if something doesn't speed up or slow down in rotation, then their angular acceleration is 0. Okay, now let's get back to where we left, and then of course continue with some other notes if there is any. Remember the definition, and of course it's been in WSATA recently as well. It says angular acceleration. It is the time rate of change of angular speed. It is expressed in radian per second, or you can simply just say radian per second squared. That is first. Second, and here's the equation. What is the equation? Average angular acceleration, you can say omega phi, change in angular speed divided by delta time. That is omega final minus initial divided by delta t. Good. Now take a look. Excuse me. Take a look at these study tips. These are very important. The first one says angular acceleration is a vector quantity, and we said that. If the rotation is clockwise, and let's say if the acceleration is clockwise, then it's positive. Oops. If the rotation is counterclockwise and speeding up, that'll be positive. I hope I said it correctly. Let me say it one more time. If the angular acceleration is counterclockwise, it is positive. If it is clockwise, it is negative. But remember this. We said, if the object is speeding up, angular acceleration and angular speed will have the same direction. But if or during slowing down, they will be in opposite direction. The second point that we have says omega initial is 0 if the object starts from rest. It is 0 if an omega final will be 0 if the object comes to a stop or comes to a rest. We also said that during speeding up, acceleration will be in the same direction as the angular speed. So these two will always be, for example, positive. They will be both positive if the rotation is counterclockwise, and they will be both negative if the rotation is clockwise. But the good thing is this, like we don't have any questions in the book where the object is rotating clockwise, whether speeding up or slowing down. So the only thing that we have, like the objects will always rotate counterclockwise, unless if it is specifically stated, which up to this point we don't have anything similar to that. Okay, the next thing is this. When an object is slowing down, like we said, or deceleration, don't be surprised if you see this word, that is grade 11, says if it comes to a stop, or like when will it slow down? When you see these words, that means it is going to slow down. Like for example, it is going to or comes to a stop, or when brakes are applied, you can say. And then, of course, we can say the average acceleration or the angular acceleration will be in opposite direction to the angular speed. So we can say if the angular speed is counterclockwise or positive, the acceleration will be negative and vice versa. Do you remember the other point we said? The angular acceleration will be zero. When will there be zero angular acceleration? If the angular speed remains constant, uniform, or doesn't change. All these words or keywords means the angular acceleration will be zero. So what are the things that have zero angular acceleration? We said the angular acceleration will be zero for the clock hands, second hand, minute hand, hour hand. Earth is rotation and revolution as well. So these are all about angular acceleration. I want to take a look at this definition. Even if you did not memorize the definition, you can always remember the equation to help you choose the correct answer. It says it is the time rate, and we've learned that whenever it says the time rate, that means something divided by the time. Well done. It says the time rate of change of angular speed. Change of angular speed. Just write change delta omega or change in angular speed. Isn't this equation for angular acceleration? Yes. So now, of course, it's tangential, linear, whatever. So it is angular acceleration. That is how you can get the answer correct or get the answer right. The second question that we have says the rate of change of angular displacement is not the same as the previous one, but this time this is the symbol, and that is the answer for angular acceleration. Now, I think it is time to solve a question here. Once again, if the directions are mentioned, we'll just consider the directions. What do we do if the directions are not mentioned? We'll just pretend, like we'll play whatever. So we just don't talk about the direction. Remember that. So here says what? A car's tire rotates an initial, or let's say an initial angular speed of this much. Car's tire rotates an initial angular speed, so this is omega initial. The driver accelerates. So accelerate here, it means speeds up, right? Very good. After 3.5 seconds, this is delta t, yes? The tire's angular speed is this much. So we agree that this is omega final. What is the tire's average angular acceleration during this 3.5 second time interval? So once again, we've learned that angular acceleration, it is equal to angular omega final minus omega initial divided by delta t. Excellent. So what is omega final? It says 28 minus what is omega initial? That is 21.5 divided by the time, which is 3.5. So you do the math, of course, you're going to get 1.9, that is radian per second squared. Don't forget the squared here. That is how easy you can do this question here. Okay. Now the next thing we have is a table. Remember, tables are like bonus marks. I've told you this before and I'll tell you again. These are the easiest question, and of course you can never ever let these 2 marks go on waste. Make sure you just take it. Okay, so here's what we have. Angular or average angular acceleration, that's angular speed. By the way, this is like the whole change in angular speed. Yani. We don't have initial and final. It's just the whole thing is ready, the difference or the change. And that is delta t. What is the first question here? Average is unknown, so just go ahead and do that. So average angular acceleration, that is change in angular speed, divide by the time, you just do the math and that's it. The second one, you could do or find the angular or the omega. Now, if you just cross multiply this equation here, change in angular speed, it is equal to angular acceleration times delta t. Once again, do the math and of course you will just get the answer right and that's it. Now, what about this one here? I would like this part C here. And the reason why I like this one, because there is a riv in the question here. So what do I do here? Well, because the angular acceleration is not given, this is part C. We'll say angular acceleration, again, it is change in angular speed divided by delta t, yes? But what is the angular change in angular speed that is given? First of all, it is negative. So here's negative 1.2, and it is given in riv, and the time that we have, it is 1.2 seconds. Now, of course, you've learned that every riv, it is equal to what? It is equal to 2 pi radian. Okay, now this 1.2 and 1.2 cancels out. So that is 2 pi radian, you can see here. Okay, so because this is the angular acceleration here, so can I just say, for example, so it is going to be negative, we can say negative 2 pi, that is radian per second squared. That is the angular acceleration here. And of course, you can convert the pi into a number. That would be negative 2 times 3.14. And then, of course, you can convert that into a number. Then you will get negative 6.28. And that is going to be radian per second squared. And that is how you can do that very easily. Okay, now here there are more Wazari questions. I will leave these questions for you to practice them. All right, now here's one thing that perhaps maybe, here's one thing that I would like to go through. Okay, now what are we going to talk about here? It says what? Says, or that is a study tip, says the angular speed, the angular acceleration of a rigid body revolving around or about itself. So I want you to think about, for example, let's say a disk or maybe a plate, let's say. Now, I want you to think about the wheel of a car. As a matter of fact, let's just think about a disk or maybe a plate, let's say, it doesn't matter. So here we have a plate, a solid plate, for example. Okay, now this is the center of the plate, or you can say the axis of rotation if you ever rotate that plate. Let's just say we're going to take 2 points here. That is point A, let's say, it has a certain radius. We can call this point RA. And then we'll take another point, let's say at the rim or the edge of this plate, and let's call this one point B. And point B, of course, has a larger or a different radius. Can I call this one RB? It's always from the point to the axis of rotation. So here's the thing. Now I want you to do this one on your own at the point here. Perhaps maybe I'll try to do that. Let's say I'll use an example too in a second. But here's the thing. Let's just say, what do you think will happen if we start rotating this table here? So here's the table that we have. What do you think will happen if I start rotating this table? Now you know that no matter how many points, or you can see that these points are always moving together, yes or no? Yes. So regardless whether the point is close to the center or far the center, once you're moving the circle, the object together, all these points are always moving together. Can one point move faster than the other point ever? The answer is no. So you can use any other examples here. Let me use another example maybe. Actually, as a matter of fact, maybe not at this point here. Okay, well, why not? Here, take a look. Okay. Let's say I have this one here. Let's say this is a solid object. That is not a curriculum. Yalla day. I will not use this one. Imagine this, Kaka. So an object is moving, okay? So we can take 2 points, you can take 3 points, you can take 10 points, it doesn't matter. No matter how many points you're taking, right, whether you're rotating the object slow or fast, it doesn't matter. The points will always rotate together. Well, what does it mean if the points always rotate together? That means they will have, so based on this, we can say, just for hard or rigid objects, when an object is rotating, we can say all their angular quantities will always be the same. What do I mean? That means the angular displacement for point A, it is going to be exactly the same for point B. You might say, how? And I'll explain in a bit. And then if all their angular quantities, we can say, that means their angular speed or the angular speed for point A, it is going to be exactly the same for angular speed of point B. So there's the angular acceleration here. What if we take more than 1 point, 2 points? Then of course, all the points, you will see that they will always have the same angular quantity, or you can say all their angular quantities, will be the same. Will be the same. Let me tell you why will it be the same. Imagine this is point A, of course. After a little bit of rotation, point A might get to this point here. And then point B, right, I should have used this one here. This is point A after a little bit of rotation. You might say, Mr. But isn't it like point B is traveling a bigger of an arc of length? I would say yes, that is true. So let's just say we want to find the angular displacement for point A here. It is equal to the arc length divided by the radius. Is that true? Yes. So as you can see here, we'll use some numbers here as well now. So let's just say that the radius for point A, let's just say it is 2 centimeter, could be even 2 meter, doesn't matter. And the arc length that is traveled by this point A, let's just say that is 2 as well. Okay, so if I use, let's say 2 over 2, I'll get 1 radian. Now, what about the angular displacement for point B? Again, that is arc length divided by the radius. But look, what is the arc length of point B here? It is true that the arc length is way larger than point A. Can I say, let's just use some numbers here. Can I say this is about twice of the arc length for point A? Yes, so if it is twice, we'll just use 4. What about the radius here? Can I also say the radius of point B? Maybe I didn't draw exact line here, but because the radius of point B is larger than the radius of point A, I can say radius of point B is about 4 as well. So you can see that these are, if the arc length, for example, is bigger, the radius is also bigger, so these two will always kind of like cancel the effect of one another, so we will always get the same angular displacement. So let me repeat this one more time. It is true that when we rotate an object, it is true that the arc length for point B will be larger, but because the radius of point B, it is larger as well, so these two large numbers cancel the effect of one another, so we'll get the same thing here. This is going to be in radian and radian. And we know that if they have the same angular displacement, their angular speed is equal to angular displacement over the time too. So if their angular displacement is the same, they take the same time to rotate because they will all rotate together. So clearly we can say their angular speed is also going to be the same here. So now let's summarize what I have just said. And this also been in Uzadi many times. When a rigid object is rotating, all the points on that rigid body, once it is rotating, will always have the same angular displacement, the same angular speed, and the same angular acceleration as well. So here's another question. Well, what will happen if they do not have the same angular displacement, speed, or acceleration, angular quantities, of course? Then imagine this. How can we ever make one point move faster than another? Imagine if point B or point A is at this point here, but here's point A, but point B is still left at this point. So what do you think will happen to the shape of the object in that case? Of course, the shape of the object, it is going to be deformed. And then if the shape is deformed, that means the object is not rigid anymore. So once again, think of a plate. If you rotate the plate, all the points will have the same point. But now think about, let's say, a pizza dough. Now, because that is not rigid, you can stretch any part, for example, and then you can make one point move past another point because it is stretchy, because the shape is not rigid. But imagine if you do that, stretch one part, let's say, different from the other part, what do you think will happen to the shape? Of course, the shape is going to be deformed because the object is not rigid anymore. So I hope that was easy enough to understand at this point here. So let's get back to this point. We'll say, when a rigid body revolves about itself, remember this, all points share the same angular displacement, delta theta. All the points here, for example, this could be an example here. No matter how many points you take, here we took 2 points, or you can take 3 points, doesn't matter. We can also say all points share the same angular speed. All the points share the same angular acceleration. Why it is very important to have the same angular quantities is because of this. We can say this uniformity in angular motion is essential. It's very important to maintain the body's rigidity, to keep rigid or to stay rigid. If not, then of course, just like seen in objects like bicycle wheel and Ferris wheel, if the object is not rigid, then clearly you cannot use the bicycle wheel. You cannot, let's say, get on a Ferris wheel because it might change shape or collapse at any point, let's say. And then point number 3, I would skip this point for now. I'll get back to this later once we study the relation between angular and translational. But let's say go to the next point here. Says, What happens if points on the rotating wheel do not have the same angular speed? We'll say the shape, you can say, or the body will lose rigidity. That is one thing, so it is no longer rigid. And then the second point, we'll say the shape will deform. So if we summarize what we have said, that we said all their angular quantities consistent or are consistent among all the points have the same angular displacement, same angular speed, and same angular acceleration. This is related to point number 3. We'll get back to this later. Now we have a question chapter review. This has been in Wuzari as well many times. It says when a wheel rotates about a fixed axis, do all the points on the wheel have the same angular speed? All right. For example, let's say we take 2 points. Does the angular speed of point B and point A and B are the same? The answer is yes, right? What will happen if they don't have the same angular speed? We'll say the shape will lose rigidity or the shape will deform. Well done. All right. All right, I think we'll end the session up to this point, let's say at this point. Next time, inshallah, we'll talk about the relation between, let's say, linear quantities or variables and angular quantities, because we'll talk about the 4 equations of motion that you've studied in grade 11, which is going to be very interesting. But before I let you go, let me just have a quick summary of what we have studied today. First thing we started was we talked about the angular speed of the clock's hand, and then we said the clock's hand have a constant angular speed. They do not speed up or slow down. And then we used to find the angular speed of each of the hands, second hand, minute hand, and hour hand, and also for Earth's rotation and revolution. How did we find the angular speed? We always said that 2 rev divided by the time that they take, whether if it is second hand, minute, or whatever. That is first. Second, after that, we learned about angular acceleration. We said it is the time rate of change of angular speed. In other words, you can say angular acceleration, it is omega final minus initial divided by delta time, and it was measured in radian per second squared. We also gave some keywords. We said if an object does not speed up or slow down in rotation, the angular acceleration will be 0. And then the last thing that we've mentioned, we said that for a rigid object, once it is rotating, no matter how many points we take on that rigid object, they will always have the same angular speed, angular acceleration, and angular displacement. What happens if they don't? Then the shape will lose rigidity. It is not, let's say, the shape will, let's say, will lose rigidity, or you can say the shape will deform. And keep practicing. Remember, I left some of the Wuzari questions for you to practice them. And wish you the best of luck. I'll see you next time. Assalamu alaikum wa rahmatullah.